The spread of large glazed surfaces in the building field has been allowed thanks to the development of insulating glazing units called IGUs. On average, in the building field, 25 to 35% of heat is lost through the walls, and 40% of this amount is lost through the windows. Therefore, adopting highly insulated windows can play a pivotal role to improve the building energy efficiency. Currently, the use of IGUs in building envelopes is a standard practice in most countries, ranging from warm to cold climates, thanks to their capabilities to couple the glass transparency with low thermal transmittance. Basically, an insulating glazing unit consists of an assembly of 2 or 3 glass panes spaced apart and sealed with a sealant to appear as a single unit. The resulting intermediate cavity is filled with dry air or gas to reduce the heat fluxes through the window. From a technological point of view, the main components of an IGU are the glass panes, the spacer, the desiccant, the filling, and the sealant. Starting from the glass, depending on the glass adopted, IGUs can meet sound control requirements, seismic requirements, bullet resistance, hurricane and blast resistance, impact resistance, and energy codes. Moreover, by combining laminated glass products, tinted glass, coated glass, silk screens patterns, and others, a wide variety of insulating glass configurations can be realized to meet several aesthetic and performance needs. Usually, the different surfaces of the glazed elements are identified through different numbers defined from outside to inside as follows. Surface 1 is the glass side that faces the outdoor environment. Surface 2 is the other side of the outer glass pane. Surface 3 is the glass side of the inner glass pane that faces the cavity. Surface 4 is the glass side that faces the indoor environment. This distinction is fundamental, for example, to identify the coated surface of a coated glass. The second fundamental component of an IGU is the spacer. The spacer defines the width of the gap between the glass panes, usually comprised between 6 and 20 mm, provides mechanical resistance of the unit, and plays a fundamental role in the heat transfer through the IGU edges. Over the years, the glass industry has moved from traditional aluminum spacers to the so-called warm edge spacers. Unlike the aluminum spacers, the warm edge spacers are characterized by lower conductivity values. This property allows, on the one hand, to reduce the heat flux through the IGU edges, and on the other hand, to reduce the condensation risk of the edge. The warm edge spacers are usually realized in plastic materials such as polycarbonates, polypropylene, and others, combined with the low metal shims. Usually the spacers are cut to a specific size and are filled with desiccants such as silica gel or zeolite to absorb the water vapor and avoid condensation. To provide the right shape, the spacers can be joined using corner keys or can be directly bent. Using the corner keys slightly reduces the overall insulation due to the joints between the 4 parts of the spacer. Instead, in the so-called bent frame, the spacer is directly bent, reducing the number of joints from 4 to 1. The connection between the spacer and the glass panes is realized by using a primary sealant, such as butyl, applied to the sides of the spacer bars. The glass panes and the spacers are then pressed with an automatic presser, and finally a secondary sealant, such as polysulfide or silicone, is applied along the sides of the whole unit. While the primary sealant is adopted to fix the IGU components during the assembly phase, the secondary sealant protects the cavity from moisture or water and from chemical attack caused by cleaning products. The key features of the sealant are adhesion, elasticity, durability, and low moisture transmission rate. Another key component is cavity, which affects the thermal performance of the IGU depending on its width and on the filling. According to the filling gas adopted, 3 different macro types of IGUs can be identified. The most common and cheap solution adopts simply dry air as filling. Thanks to a drying unit, the air moisture is removed to avoid the condensation on the cavity-facing glass surfaces, namely surfaces 2 and 3. The second type of filling is based on inert gas, such as, for example, argon, krypton, and xenon. On the one hand, these gases are more performing compared to dry air, as shown in this graph, but on the other side, they are more expensive. Regardless of the filling adopted, the IGU can be classified also depending on the number of cavities defined. The most widespread solution are the so-called double glazing unit, IGU, which are composed of 2 glass panes and a single cavity. This solution can offer U values ranging between 3.3 and 1 watt per square meter Kelvin degree when coated glass are adopted. Nevertheless, mainly in cold climates, the thermal transmittance can be further reduced by adopting a triple glazing unit, TGU, which is composed of 3 glass panes and 2 distinguished cavities. This additional layer can reduce the thermal transmittance up to 0.4 watt per square meter Kelvin degree, while increasing the thickness and the weight of the IGU. New technological developments are leading to a third type of IGU, which takes advantage of the low transmittance of vacuum. These systems are usually defined VIG, vacuum insulated glazing. Despite the high thermal performances, around 0.3 watt per square meter Kelvin degree in very low thicknesses, around 6-7 millimeters, the differential pressure between outside and inside the cavity creates a high pre-existing stress during fabrication and hence makes the units more susceptible to breakage. The use of IGUs has driven the spread of large glazed windows. Starting from the concepts described in this lecture, many different insulating glazing units can be developed by coupling specific coatings to change their thermal optical properties, as better described in a dedicated video. Moreover, a promising field to improve the IGU's performances regards the adaptive coatings, which allows to vary the IGU properties according to specific external stimuli.